Welcome everyone to today's webinar, which is part of the Young Scholars webinar series on climate change, macroeconomics, and finance organized by the E-Access Forum. My name is Alice Nijenhuis, and I'd also like to welcome our PhD committee. Before we get started, I'd like to announce that we have a new call for papers for the Young Scholars webinar series. We will be drawing from the submitted papers for the 2025 winter term, so please take a look at the homepage of the E-Access website at www.e-access.org for more details. You could also send your submissions directly to info@eaccess.org. In today's webinar, I'm very pleased to introduce Oliver Wang, who will discuss his research with Stefano Giglio, Teresa Kukler, and Johannes Strubel on how biodiversity loss impacts economic production and future growth potential by affecting essential ecosystem services. Oliver Wang is an assistant professor of finance at New York University's Stern School of Business, and he conducts research in macroeconomics, financial intermediation, and climate finance. His recent work studies the interplay between biodiversity loss and economic activity, as well as the effect of common ownership by large institutional investors on portfolio companies' decarbonization. He has also analyzed how trends and cyclical movements in interest rates affect bank stability and the competition between banks and non-banks. The policy determinants and the long-run consequence of zombie lending is another area that he has been studying, as well as the link between rising product market concentration and monetary policy transmission. Olivier received his Bachelor of Arts in Mathematics and his Master of Arts in Economics from École Normale Supérieure and his PhD in Economics from MIT in 2019. I would want to welcome you all to this E-Access webinar. We will have time for questions after the presentation, but Olivier also indicated that if you have any questions you want to ask in the middle, let's say if you don't understand some of the notation of his theoretical framework, you're more than encouraged to ask the question. I'll try to draw Olivier's attention so he can answer it at the spot. So to ask questions, please use the Q&A function at the bottom of the screen. And I would like to tell you all, I hope you will enjoy the talk. I would like to hand the floor now to the moderator, to the speaker, Olivier Wang. The floor is yours. We're much looking forward to hearing what you have to say about this important paper.
Thank you so much, Elisa, and thank you everybody for having us present this. This is a great forum. So let's get started. So the motivation, it's a series on climate economics and finance. And so recently, there's of course a lot of interest in understanding climate change. But we think, one kind of missing piece of kind of the planetary boundaries, the interaction between economic activity and the state of the Earth is this notion of biodiversity. And in fact, policymakers and academics have been studying it, especially in ecology. Policymakers are starting to draw attention to this. And so the kind of perspective we're going to take here is to view, biodiversity, nature, as one, factor of production that's affected by human activity and that kind of also delivers services. And so the term for this, coming from the ecology literature, is ecosystem services. And so if you think, that nature is providing these services that are valuable, not just for consumption, not just because we like biodiversity per se, which could be a big factor, but here we're going to focus on the production side. Then destroying nature would mean destroying the economy. And, the ECB in particular has been pushing this message and, drawing attention to that topic. And so this paper, the goal is kind of first theoretical is to take a first step in modeling the dynamics of biodiversity loss, the consequences for the economy, and the interactions. So just like for climate, economic activity affects emissions, and emissions kind of have damages on economic activity. Here it's going to be the same with biodiversity, and I'm going to try to highlight what's common and what's different from climate. And towards the end, I'm also going to show you some new empirical work that kind of tries to test some of the implications of the framework. So most of the paper is going to be, maybe a little bit unusual, in climate economics and finance. Here is kind of trying to propose a new theoretical framework that's not too complex, so that it's flexible but also manageable. Not yet a huge quantitative machine, because we view this as more like this first step. And so the specification, we're going to look at how species and their diversity interact to produce, ecosystem services. And so we're going to build a lot on the ecology literature. So we read tons of these papers, and it's very interesting. They have a lot of very interesting concepts that we try to map to, more well-known economic concepts in the theory of production. And after that, we're going to model the effects of human activity. So the other way around, especially land use, which we view as the main factor, affecting biodiversity on, these species. So then we're going to derive some qualitative prediction and test the implications. And really, one key idea is that nature is not just one monolithic natural capital. It's a very complex ecosystem with interactions between species at different layers. Okay, so we're going to simplify and kind of look at the minimal complexity that we think is key to have, but you could generalize. And the idea is kind of to treat the ecosystem a little bit like we think of in macroeconomics. It's not just one firm, and you have a whole supply chain or an input-output network. So some suppliers buy input of others and so on, and so you may have these complex interactions that makes some sectors, some firms in some sectors really key for the whole system. And that's our view of biodiversity as well. And I'm going to talk briefly of implications for policy design. So we think this is a good framework to kind of start thinking about this. We're working on follow-ups too, but happy to talk more. So first, what's biodiversity? So it means many, many things. And so you could view biodiversity as, there are some diversity in terms of, some very fundamental objects like genes or species or ecosystems. And so the literature talks about this. In this paper, we're going to focus on something that's kind of easier to also measure, which is diversity of species. So that's something that, ecologists keep track of, kind of the strength of the habitat, how many species are remaining. Also within the species, the number of individuals or the kind of biomass or abundance. But of course, you could look at different conceptual levels. Okay, so and we're going to argue, based on the ecology literature, that it plays a crucial role in supporting different economic activities. Okay, so conceptually, they're kind of we're not going to separate in the model, but you could think of two different kinds of services. One is like provisioning, which is a direct, production by nature. And so the obvious thing to think of is like agriculture, okay, food, timber, but also pharmaceutical, raw materials, genetic information. There's just a lot of, there's a pool of potential, drugs that's coming from, the natural genetic stock. And then there are another kind, which is regulating and supporting services, pollination, provision of clean air and water. You could think if it interacts with climate too, wetlands kind of prevent flood damage, carbon sequestration, pest regulation, so tons of different things. The framework is going to be pretty abstract, not exactly restricting, but that's the goal, so to have something flexible. But the key thing is that you have many different functions, and they're complementary with each other, meaning the productivity of some ecosystem services also depends not only on that functions, health in terms of, how many trees, how many animals are able to do this, but also on other ones because they interact in very special ways. Like in terms of, in ecology, you would call that synergies. In economics, it's more like complement, but it means the same thing. It means it's something about, how your effectiveness, productivity depends on the other functions. Okay, so that's going to be something key to capture. And so we begin from, this aggregate production function that's very standard in economics, where y, the output, is produced from different factors x. So these would be the usual factors like physical capital, labor. But then we're kind of want to focus on this, so isolating this other factor E, which is the ecosystem services. Now, in principle, you could do something kind of the richer model would have, that itself is broken down into multiple functions, and that can be more or less substitutable with, human factors of production. So you could have a whole network. Here we're gonna do like something, the simpler version that still keeps some of the interesting complexity, but without going too far yet. Which is, okay, we have this aggregate ecosystem services, and we're gonna say, okay, that is produced from, different functions. And the key is that there's a hierarchy. So you have different functions, like these different systems I talked about, pollination, pest control, and so on. And these are given, these are the functional groups. So it's not like they're gonna disappear or something or grow, these are the different functions, but these functions are provided by many different species within the function. And so a loss of biodiversity is going to be, well, within a function, you're losing a lot, say 50% of the species that do this. So the pollinators, for instance. And now the impact of this also depends on, what's happening to other functions, agriculture, and so on. Okay, so that's going to be the hierarchical model. You have these functions, these big blocks, and within that, you have many species that can provide these functions. But crucially, these species are not all equivalent either. So in terms of economics, we say they're not perfect substitutes necessarily. So that's the hierarchical visualization. You have the goal is to produce output. Again, we're not really talking about utility from having more species, although, of course, that's something important. But here, we're just taking a pure economic production viewpoint. And then this factor E is kind of coming from an aggregate of ecosystem functions. So G, E1, EG, and so on. And so that's on the right, you have the kind of aggregator that maps these different functions to the aggregate E. Again, we're using something very standard in macro in trade, which is called the constant elasticity of substitution aggregator, which is I put these together and they're aggregated, and the sigma parameter kind of telling you how substitutable they are. And we're going to argue sigma is something low, okay? Lower than 1, meaning, they are complements and not substitutes. And the meaning is that, it's just very hard to replace just by improving one. If the other one is lost, it's not going to do much good, So it's important to have everything working well. You need, different healthy ecosystem services. And then within each function G, okay, this is this EG in the middle, this is provided by many species. And so there's a number of surviving species SG, okay, and that's going to be affected by land use and so on. And then for each species, you have some, so the generic term is abundance, but you could think of number of individuals if it's animals, or like biomass if it's plants. But abundance is kind of a common term to say, okay, within each species, you could have more or less just, individuals or biomass. And then within the function, it's very different. Within a function, it's not, you have substitution. So, different species can provide the same service. And so that's parameterized by this other elasticity of substitution, epsilon G. And that thing is high, but maybe not infinite. Again, the fact that it's high means that, different species are kind of replaceable. If we think of, a single function that they're producing. But different functions, cannot replace each other. It's crucial to have them all. Okay, so now within a function, there are rich interactions. So that's where, I'm going to go very fast. But in fact, in the paper, we give a thorough review of the ecology literature and trying to map it to economic concepts. And the two key ideas that come out from this literature, and they have many ways to estimate it, identification. So it's interesting how they kind of encounter similar challenges as in economics. The first one is biodiversity productivity. So this says that the productivity in terms of how many ecosystem services, the amount of services that you can provide, and therefore, economic production eventually, that's an increasing function of biodiversity. Okay, so not just of the number of abundance, okay, because having more species and so on is good per se, but also diversity itself is good. And so that's an increasing function of biodiversity, but it's concave, meaning at some point, the marginal return to having more diversity gets lower and lower, smaller and smaller if you have a lot. But that also means that if you deplete a lot of your ecosystem, lose a lot of species, then the marginal impact of losing the next one is going to be stronger and stronger. So that's one source of concavity. And so the idea, how they call it in ecology, is niche differentiation. And so here I'm quoting from some ecology paper, which says that, okay, species, they use different resources, or they use the same resources or, eat the same food, but at different times or points in space. So for instance, some are going to live during the night, some during the day. And so they are not perfect substitutes. And if you have more different kinds of species doing the same service, providing the same ecosystem service, it's good to have many different kinds because they use resources in a more efficient way by kind of naturally through natural selection, kind of having their own little niche and not competing too much with the other ones. So they're doing similar tasks, but there's kind of a division of labor, if you think of economic terms. And another analogy is that in trade, for instance, we like the leading models of trade now are about where we kind of love variety because you have different varieties of the same good and they're not exactly the same, and that generates welfare gains and motives for trade between countries. It's not just about comparative advantage in very different goods anymore. So the second part is biodiversity stability. It's more about how do you think about resilience to risks. So risk could come from human stress or environmental stress or random shocks like diseases. And so the idea here is that having more diversity is good because you create some redundancy and that acts as insurance. So it's a little bit like in finance, you would think of a portfolio. And so you want to have some diversity because diversity also means that they are imperfectly correlated because they provide similar functions, but not exactly using this, maybe some are immune to some diseases and so on. And so that acts as insurance. And so if you lose diversity, you're more exposed to future shocks. Okay, so now mathematically, within a function G, so think of, again, one function pollination, and each function has this breakdown. You have SG species, and SG is going to vary over time. So initially you start with a lot and you have these losses. Of course, in some case you can gain, but we view it as a very long-term thing where species are created through natural selection over the very long term. But at these human scales that we're looking at, given the tremendous speed of biodiversity loss, think of species or the number of species kind of falls. Okay. And within each species, you have this abundance. Okay, again, it's biomass for plants and more like individuals for animals. But this is just going to be N. And so each species is indexed by I. And there's this Ni. And then the production of the ecosystem service G, this function, is this aggregator of the different species' abundance. And they're highly substitutable, meaning, they're not complement. The elasticity of substitution, which kind of tells you, how replaceable with each other they are in terms of production, is above 1, but it's not infinite. Okay? Now, biodiversity loss, as I said, is like you're losing a number of species. Okay, so that's going to be the fundamental shock. Now, it could be driven by human activity, so we're going to come back to this. But for now, just view it as it's falling for some reason. And you can calibrate to what ecologists estimate. So we always see these numbers, we lost 50%, 30%, depending on the country, depending on the function, depending on the group. But here, suppose, you start from some high level S bar, that would be, just like in climate, we say pre-industrial. So this would be some initial level. And then little s is the fraction that remains over time. And so that falls over time. So biodiversity loss is to say this little s is below 1. So you kind of have a number of species that's below the initial and maximal level. And so when that happens, you need to keep track of another thing, which is you have to think, and there's whole ecology literature about this, which is, well, what happens to the surviving species? They're kind of, because these species within this function, one point is that they perform similar functions and they share habitat, and maybe they are not exactly the same. So some live by day, some by night, but there are some compensation too. So one direct effect is that, okay, some species disappear, and so that has an impact on total abundance or biomass. The second indirect effect is that the other species presumably are going to partially grow because there are more resources for them. And so in reduced form, we kind of model this as saying, okay, there's a parameter alpha that's going to tell you the extent of compensatory growth, okay, by the remaining species. So that the abundance of the survivors is not necessarily a given, but depends on how many species are surviving. Okay, so I'm going to kind of illustrate this even more with the graph, but that would be this equation 3. Okay, so here this is breaking it further. So to explain, alpha, you can view it as some parameter and it depends on the function. It's kind of about the ecosystem. It's between 0 and 1. And so you can think in the very short run, alpha should be 1. So meaning there's no compensatory growth because they don't have time to kind of offset the loss of some species. Okay, so in the very short run, some disappear. There are some disease or, they were destroyed by some human activity. And then the other ones, they still have their number of individuals or their biomass. And then eventually in the long run, alpha is going to fall. So not necessarily to 0, there's some steady state, but suppose it's 0, that would be the extreme case. Then that would mean that the remaining ones are going to grow so that, total function-wide abundance is conserved, it's unchanged. So that would be something like, suppose you have 2 species and one disappears, and eventually the other one kind of takes advantage of this and grows back. And so in terms of individuals, you end up with the same number, but now it's less diverse. It's like you had 100 animals, 50-50, and now you have 100 just of one species. Okay, but that's something that ecologists estimate. And so here I'm giving the extreme case 1-0 to illustrate. Okay, and we're going to work with this reduced form. There's a whole theoretical, more applied math ecology literature, which models this process where we compete for resources. So it's these Lotka-Volterra competitive models with many species. They're kind of hard to work with, but eventually you reach some steady state and it looks like this. Okay, so we're just going to work with this. So now combining all together, now at the level of function, what happens when you lose species? So you see this equation 5 has 2 terms. One is there's a term that increases with the number, the biodiversity, little s, with an exponent v. Okay, this v is for variety. So here is v is given by 1 over epsilon minus 1. Okay, so don't pay too much attention to the precise form, but this is saying this would be 0 if they are perfect substitutes. Epsilon goes to infinity. So if the species are exactly equivalent, it's just a label. Some are called bees and some something else. But in the end, they're exactly the same in terms of the services they produce. There's no gain from diversity there. But if they're not exactly the same because of this niche differentiation, so not only we characterize them as different species, but effectively they use resources, not exactly the same. So having more of them is better per se, which is like the love of variety effects in economic models. When you have more different firms and so on, then there's some gain from this. But then that means that when you lose in terms of biodiversity, you're losing from this. And by how much? By this exponent. This is the elasticity of the productivity to the diversity. Now, the second part in equation 5 is this community resilience, which is capturing this compensatory growth. Okay, so and eventually you can rewrite this with equation 6, which is even more reduced one, which says, okay, ecosystem services are kind of a max level, E bar, times biodiversity S within that function, power phi, and phi has these 2 components. And these 2 components from biodiversity could be, either from the love of variety effect, V, or from this alpha. And so you see alpha here is saying, remember alpha equals 1 means there's no kind of compensatory growth. So that's when biodiversity is very valuable. And over time, it can decrease a little bit because the remaining ones are going to grow back a little bit. And so if you think in the very long run, they grow back completely to kind of completely offset the decline in abundance, because you go from 100, you kill 50, and then you still have 50 individuals, but they kind of grow back to 100. Then the only gain from diversity would be from the V, would be that, well, now you have 100, but they are only from one single species, so you lose this niche differentiation because now they compete with each other more starkly. It was better to have different species because some would live during the day and some during the night. But now you have more during the day, so they grew because they have more food left. But within the day they kind of hurt each other and so on. But if alpha doesn't go to zero, you have one term there, which is you lost some diversity, and it was not fully offset by the remaining ones. And that's what ecologists estimate and find empirical. It's never fully offset. And so a value to keep in mind is something like 0.3, 0.5 for the phi, capturing both these parts. Okay, it depends on the function. So just like in economics, you have different parameters for different functions, viewed as like different sectors of the economy. And so here it's just showing, so this introduces some concavity, okay, which is focusing on one function. Here on the x-axis, I have biodiversity going from 0 to 1. Remember, 1 is like you have the maximal number of species because we're normalizing by this maximal. And when you fall, you see if phi is very high, you fall in a linear way. So it's bad, but it's not concave. It's uniformly bad. It's bad whether you go from 1 to 0.9 or from 0.3 to 0.2. Whereas if you use reasonable values of phi coming from these other estimates that I talked about, well, you get something more like 0.3, and it's very concave. And this is saying that initially you're very resilient. Initially, it doesn't matter too much. It's very flat, although not with a slope of 0. It's like initially you have some impact, but the impact is going to be stronger and stronger as you lose more species. As you move to the left, the slope is getting stronger and stronger. So that's within a function. Now, the second key thing is that you have these synergies between functions. And like the OECD says, the loss in any single service in, say, any function is likely to reduce the productivity of the other ones. So this is saying that, well, they're not perfect substitutes, they kind of interact. And so your productivity depends on the other one. And so here, this is captured by this function, which is, if you look at the aggregate level, I'm going to aggregate these different functions, but they interact in a very particular way, which is their elasticity of substitution sigma is lower than 1. Okay, why? So, papers also in ecology try to estimate these kind of synergistic effects. So now they have to be very careful and focus, on two functions. And here we have, we kind of have a more macro view looking at many different functions. But if you take these numbers, if you look at pollination and pest control, for instance, well, this is saying they interact and their joint effect, if you improve both of them, you improve your yield increases by 23%, just focusing on agriculture. And if you increase one of them without the other, you get 7 and 6%, so much smaller. So if you use the model, and we do that to back out, some effective elasticity of substitution that's implied by this number, kind of very low, it's 0.1. And you could see, if this were very high, then the joint effect, would be something, and the single contribution would be just, say, half and half of the joint effect. So suppose it's 23, the single contribution would be, 12 and 11. And that would be like, oh, there's not much complementarity, because it's just, you're increasing one, it's good. You're increasing the other, but they don't really, affect each other. And conversely, if you had the joint effect 23, but the single contribution were like very, very small, like 0 and 0, it would mean that, well, you're only getting the joint effect if you increase everything at the same time. So that would be sigma equals 0. But it turns out, in this context, sigma is effectively very low. That may depend on the pairs of functions that you look like. So we're not going to always take sigma 0.1, but these are actually the best numbers we could find. But we're going to look at a range where, it makes sense to think sigma is lower than 1. Okay, so now going back to this aggregation, so you go from the bottom to number of species within a function to the production of that function to the aggregate ecosystem services to the economic production Y. And so what do you get? So the first thing is that you can combine these two concavities. And so we call it a double concavity to say when you lose species, so biodiversity loss, there's like two reasons why initially it has very little impact, but it can have a very strong impact once you reach sort of tipping point. It's where start being very scarce. So the first thing is that it's concave within a function. Okay, so these are the graphs I showed you with different values of phi going from 0.9, 0.5, and 3. And so 0.3 was much more concave, and that's a more likely number to use. Then if you aggregate different ecosystem functions, it amplifies the concavity because they're complement. And so just intuitively, it means that if you're losing a lot of species in something where you started with a lot, and it's not the scarce constraining factor, then it's not going to have much of an impact. But if you lose species in a function that's already depleted, it has a much stronger impact. Now, naturally, you could think that if some human process, they tend to kill species, deplete biodiversity, it's going to keep going in that direction, and it's going to create these big imbalances between functions. Just as a byproduct of human activity, some functions are going to be much more affected than the others, and we're going to run into that problem where some are very scarce, some are very abundant, but it's not recompensating. So the fact that, and maybe protecting some that we care about may not have such a big return because they're not the ones that should be protected. So of course, usually we protect the ones that are more endangered, but it tells you it's a complicated multidimensional view. And so how does it look like? So now on the x-axis, I have species in one function, and here the max was 100, and so you start losing. And this is showing you so that the dashed line is what happens within that function. So we have some concavity there. But then the red and purple lines are showing you at the aggregate level what it does. And it's even more concave because of this complementarity between functions. And to visualize the extreme case, suppose sigma goes to 0. So that would be what in economics you call Leontief, which is, the only thing that matters is the minimal function. And then in that case, suppose, some other functions were already scarce. And so then if you go in that function G from 100 to 20, it has 0 impact. That's the extreme case of sigma going to 0. It doesn't affect ecosystem services at all because you're actually constrained by other functions that were already depleted for some reason. But once in this context, once you reach 10, then that function becomes like the limiting factor, the bottleneck in the production of aggregate ecosystem services, and then it falls very rapidly. So that's in an extreme case, a case of concavity, which once you pass some threshold, some tipping point, which depends on the whole nexus of all the other functions, you become very constrained. And so this resembles what in ecology is called keystone species. So you can think of keystone species, keystone functions, and species within these keystone functions or keystone species, where the impact of sun loss is very state dependent, and it can be disproportionately large relative to that species abundance. And so it could be just like an analogy is like in production networks in economics. If you think there to a first approximation, some sectors like electricity seem very small. It produces like 5% of GDP. And you would think, okay, if I lose electricity, am I going to lose 5% of GDP? Well, no, because then everything is going to collapse. So it's kind of a constraining factor. And the share in terms of total ecosystem is not reflected by the share of abundance. You have to keep track of something that we're going to call criticality in the model. Okay, there's a, I'm not going to show the expression, but you can the model gives you as a function of elasticity of substitution and the distribution of previous biodiversity losses, each species criticality, which could correspond to this example of each sector's criticality in the production network of an economy. And for instance, there's a very recent AER paper, Frank and Sudarshan, which says, okay, in India, we lost some vultures. Okay, so they have a very nice identification based on drug patents expiring. And you get an increase a huge increase in human mortality, 4% in some region, due to the collapse of some vulture population that was acting, providing what ecosystem services? Well, it was like they were eating dead animals, and so it was preventing diseases from hurting actual humans. And so once these vultures collapse, it looks like you didn't lose that much in terms of number of animals, of abundance, but it had a huge impact because they were already the only ones providing this. And over in that region, there's no like substitute either by other species, either functions, or by human technology to perform this function. So the basic message, and we kind of formalize this, but just in words, is like biodiversity loss has a very context, state, history dependent effect. Okay, it's not just which how many species are lost, but which ones. You have to keep track of the exact complementarity between functions and so on. And the model is a framework to do this. Now I'm just going through, at a high level the results, but the model can be used in a flexible way to kind of measure these things, hopefully. So the third result is that, okay, you're kind of losing species, and so that's gonna, in reality, let's consider shocks to biodiversity, where we measure from ecology databases, how many species you lost in different countries, doing different functions. So you have a vector of losses, and you want to say, okay, what happens to the whole ecosystem? And we have defined a notion of ecosystem fragility, which is, suppose you had something which can collapses, everything with a common shock. So you can always decompose, a full shock into a common shock and some idiosyncratic shocks. And so a useful measure the sensitivity to a common shock to hurting many species at the same time. So this is this DS. This is just to come up with a summary statistic. And already there, it's going to be complex. Now, in reality, it's even more complex because you are not losing species at random. It turns out that you're going to keep losing species where you already lost them because there's something in your human production function that is hurting these species more often. But if you do the simple case, okay, so first do the general case. What's the loss in ecosystem service? So this is an expression that also looks like what macroeconomists do in the production network literature. You can decompose the loss in efficiency into different terms. But here we frame it in terms of biodiversity, and kind of it means that you want to measure different things. So the first term is the direct effect of losing community abundance. So this is a direct effect where you lose some species, you lose some animals, and then you see that it depends on alpha. So if alpha is very high, it's like you didn't have any compensatory growth yet. And so there's a big impact, direct impact. It's just you lost them. So of course it has an impact, but it's not coming from the diversity per se. It's just because losing species means losing individuals. Okay. So now you could imagine that in the long run, if alpha falls a lot because of compensatory growth, that term disappears. But it depends on whether alpha is going to go to 0 or remains at 0.5, say. Now, the second term is niche differentiation. So that thing is not something that's going to disappear over time through compensatory growth, because it's fundamentally that, well, I lose some species and the other ones, they cannot replace them perfectly because of this love of variety effect, coming from this epsilon within function being lower than infinity. And again, that's something that can be estimated by the ecologist. And so this is an indirect effect due to the niche differentiation that's now less effective, coming from the first concavity. And now the third term is about imbalances between different functions, and that's the one that's going to depend on the complementarity between different functions. And this is a covariance term saying that you're going to have a larger impact if you're losing species, okay, so DSG, in functions that are already like critically depleted as parameterized by this gamma G. So gamma G here in the covariance is going to be very high if you're already a critical function. Now, gamma G itself has an expression that depends on biodiversity loss everywhere, because it's going to be a relative statement. Critical means you lost more than many others, than the other ones in relative terms, and it also depends on the complementarity. Okay, and so it depends on many things. I'm not showing the expression, but it's in the paper. And so how to decompose? Suppose, you know, we have something where we lose one species in one function, S1, and we're kind of leaving the others untouched. Okay, it's just a thought experiment. Of course, we're losing all the time everywhere, but suppose we're just shocking one. And so the total effect is going to look like this. You start, so here it's negative, you know, the ecosystem services are going to fall in this concave way. And you can decompose, and initially it's going to come from the green term, community abundance being lower, so you lost them. And maybe in the short run, you have a larger impact on this, but this vanish kind of shrinks over time. So here I'm just doing a snapshot for a given value of alpha, where remember alpha could have a short run value and a long run value. Then the blue part is saying, okay, that's the loss in terms of efficiency due to the lower niche differentiation. Now we have less variety, so it's a pure diversity effect, this one. It's like there's less variety, so it is making everything less effective because now you have more similar species competing for the common resources. And initially, you don't have any imbalance here because initially we start from a case where the other species are fine and this species is fine, and so there's no covariance term. But as you lose a lot in the species S1, you know that you're going to have a larger and larger factor which is coming from imbalances. It's like it's going to become very, very bad to keep losing species in that function. Okay, so suppose, you know, some particular thing like pest control. It's going to be very bad to keep losing this because it's going to start hurting the aggregate productivity just because it cannot be replaced elsewhere, and you're introducing this imbalance where the other ones are fine, but you lost a lot here. So if you could, you would reallocate the losses towards other functions. It would still be bad, but it would be much less bad because it would reestablish the imbalance. Okay, so what's really bad is if you keep losing in the same place because you're not reestablishing the balance, you're kind of amplifying the imbalance. So that's what the covariance term is saying. Now this decomposition, you know, gives us the general sensitivity. As I said, you can simplify by considering common shocks, which are restrictive, but it's also simpler to keep track of just one number. What's this number? We define it as fragility. This is equation 8, which is going to be the sensitivity of aggregate ecosystem services and therefore total output to a common shock. Okay, and so in the end, the expression equation 8 is going to be something pretty nice, which is kind of your weighted average of the criticality of different functions. And the criticality, again, depends on how depleted a given function is relative to all the other ones, and on the elasticity of substitution sigma, which is pretty low. Okay, so that is a framework to think of this, you know, very broad. Oops, sorry, there was a. I pressed escape by mistake, so I need to reshare. Which is, you know, why didn't you see a lot of output impact yet? Well, because you lost it where it was kind of not scarce yet. But what's happening in the background is that the fragility is increasing a lot, even though the direct effect is not seen yet. And so going further, you know, in the future, if you keep losing, and there's no reason you stop losing species if you already lost like 50%, that's going to have a huge impact because it's kind of you're reaching the very kind of steep part where it's very concave. So initially it's flat. Okay, so you need some measure of the background risk that's increasing. And that's kind of the fragility measure. Okay, so we have let me skip this. So very briefly before, you know, taking a few minutes for the empirics. Then we do something which is, okay, let's go to the next level, which is, let's look at the interaction with the economy. So for now, I just talked about what's happening to aggregate ecosystem services. We want to know what's happening to output in the end, so just GDP. And so we're again have another form of complementarity, which is called strong sustainability, which is, you know, it is difficult, at least for many functions, but, you know, so you could disaggregate even more, but we're doing the simple version here, which is, in general, it is difficult to substitute natural capital and physical capital. Okay, now technological progress may affect this, so it's a little bit of a snapshot, but, you know, think of this vulture example where, especially in developing countries, you have some functions that are provided by nature. And it's just very, very costly there to replace it and have like the same function provided by humans. And so, okay, so now you have some production benefit from having these ecosystem services being not too depleted. But, if you use more land, it's also better for production. And so you have this trade-off. So let me go very quickly. We do this intertemporal model. You could do infinite horizon, but all the insights come from, having present and future. So think of how much land do I use now? It's going to deplete biodiversity. It's going to affect my future ecosystem services and my future output. And now as a country, I need to balance the present and the future, just like in climate models. So it's going to depend on my discount rate, my effective inpatient, how much weight am I putting on the future, which is this beta. Okay, so this is some equations. Now you could, you have some function that again may come from ecology, which is telling you how land use affects biodiversity. It's going to depend on each function. And it's going to depend on, maybe it depends on how much you start from. Okay, so just a quick analogy, it resembles problems of, how optimally to extract some depletable resource like fossil fuels. But it's much more complicated because you have this multi-dimensional thing, and you may not be able to target, exactly which species do I want to preserve and which do I care less about. And then you may have this very nonlinear function, which is embedding in itself some tipping point. Maybe once you lose a lot, now it's very fragile because of this biodiversity stability within function. So I'll skip this. In the end, we kind of come up with, simple formulas. I mean, at least if we had more time, I could describe why, they're kind of simple in the end. But one result is this, okay? Under some simplifying assumption, the optimal conservation of land, which is 1 minus U, so U is the land use, is going to be given by, in that bracket, there's a delta factor here, which is telling you, the direct impact from losing, just abundance, okay, but not about biodiversity, just because if you use more land, you're also killing more individuals within each species. But then it's kind of amplified, okay, because it's thus amplified because the numerator is lower than 1, by something which depends on the fragility. And so basically, if you're very fragile, and fragility could come from many things, could come from having lost a lot of species everywhere, but also having lost them in a very imbalanced way, then optimally you should make much more effort to conserve land and therefore species, and kind of foregoing the economic benefit of land use. Now, all that is also going to depend on where the country is in terms of, how much capital they have. And so that's also something we want to test. So let me skip this. This is about fragility. This is if you could target a little bit more to different types of functions. But basically, different countries are going to be at different points of the trade-off, because different countries may have a different stock of natural capital, so kind of how many species are left there, and different, physical capital. So maybe, it's a model of convergence growth at a solo, and so maybe you want to invest a lot in capital and land to grow if you're starting from a low point. And so you have this trade-off and heterogeneity. Now, one thing also is that in the model, it's not like you have immediate impact. In fact, we write it in a way where the impact is delayed. And so if you try to measure this, again, you're not going to see an immediate impact of GDP, because what's happening is in the background, the fragility is increasing. But future shocks are going to be very damaging. And so to test the theory, we find evidence from asset prices, which are forward-looking and kind of potentially capturing the damage coming in the future. So to do this, we want to test some predictions of the model, which is biodiversity negative news are bad in terms of what investors think about future output. And we're going to measure that as a macro risk to credit default swap on the countries, so CDS spreads. But that impact is heterogeneous. It's going to be much stronger if nature is already depleted. And it's going to be much stronger if nature is the constraining factor of production, whereas it may not be so strong if the constraining factor of production is something else like scarce capital. So that's what we test empirically. So let me skip this. Data sources is described in the paper, but basically, we have the series of news, so negative biodiversity news, say, and then we look at how it impacts CDS spread on sovereign debt. Okay, so each country, we have around 90 countries. We look at their sovereign debt, and CDS are measuring the default probability perceived by the market, and so it's kind of macro risk. And when this increases, it means it's negative news for the country. And we want to know how biodiversity news from the newspapers affect the CDS spread. And so this is the table. So in the first column, you see that news are bad. Okay, the first row everywhere is positive, saying if you have bad news here, you have a higher CDS spread. So this is the convention in terms of science that we chose. Okay, so these are the positive terms. So that means higher probability of sovereign default in these countries, which we view as, it's bad at the macro level. Output is going to fall. Then the second line, second row, is the interaction between the news and the state of biodiversity. So the negative coefficients are telling you that, well, the news is less damaging if you have a high biodiversity score. And it's more damaging if you're already low on the biodiversity score that we're getting from different data sources. And the third way is saying that, well, that's the interaction with the natural capital share of wealth, which is, are you producing, is the scarce factor physical capital or natural capital? And the interaction is negative, which again says that, if the scarce factor is actually natural capital, so it's very low share, then you have a more negative impact. The CDS spread goes up by more upon negative biodiversity news. Okay, so let me conclude. So biodiversity economics and finance is a new field. We think, of course, there's been a lot of work on climate change, but it's also good to expand and kind of apply some ideas and look at what's new in other domains of, planetary boundaries. So, for instance, interactions between biodiversity and the economy. Now we're working on follow-ups where we want to put everything together, so climate and biodiversity, because obviously there are also interaction between, say, carbon sequestration or climate affecting, biodiversity itself. So you have these even richer feedback. Thank you, and looking forward to the discussion.
Thank you so much, Olivier, for your really fascinating presentation. During my PhD, I actually, studied a little bit ecosystems, so I know that your model captures all the key ecological concepts that matter. So I'm really impressed that you were able to put this into this economic framework. And I also really enjoyed seeing that you've done some empirical studies looking at how the degree of the tightness of the natural capital constraint and so on affect CDS spread. So that's great. I guess I was wondering, and that's one question on my end, and then I'll open up the questions to the floor. Right, you have this model of output where output is not only dependent on physical, let's say, capital and human capital, but also on ecological biodiversity capital, and then you split that into its hierarchical subcomponents, and you have these functions G that then capture different species that offer the same sort of ecosystem service, such as pollination or agriculture. So I guess what I was wondering is if you like what, for example, William Nordhaus has done with these integrated assessment models, that he's actually tried to somehow calibrate these theoretical models. Do you think it would be possible for you to try to calibrate this theoretical model and actually identify what these G functions are and what the different species are that are performing these G functions, and what the degree of adaptability is if one of the species declines, and whether others can fill in the gap? So I'd be really curious to hear your thoughts on that.
Yeah, no, I think we can do much more. So here, in terms of empirics measurement, we went very macro, with these summary measures.
Yes.
We are working on this. It just turns out to be a lot of data collection effort. Now, some ecology departments have done a lot, so we are using those, and we have new empirical